सुकांत का ये रख लो, लेके चल जाना.
The previous two talks really set the stage, as Dr. Naik mentioned, to talk now about a special kind of earthquakes, which is really a very societally important area of earthquake science, and that is the triggered earthquakes. And by triggered earthquakes, I would rather generalize the term to anthropogenic earthquakes. That is, earthquakes that are caused by human-induced changes. And how? What are those kind of changes? So I'll be briefly summarizing what we mean by anthropogenic seismicity. Anthropogenic seismicity basically as a result of human-induced changes that I mentioned. And these changes are brought about by a variety of human activity that are absolutely essential for the development of the economy of any country, in the activities such as conventional or unconventional energy production, oil and gas, renewable energies, geothermal, for example, and potentially environment-friendly methods related to climate change, for example, CO2 sequestration, the geological sequestration, burying of the carbon dioxide, industrial carbon dioxide into the earth to bury it basically and minimize its impact on the global warming. The need to understand anthropogenic seismicity, therefore, has become extremely important in view of the socio-economic impacts that they bring about. And they are relevant not only in India but all over the world. So I'll briefly use one of a figure very similar to the one that Somer showed. If you see the bottom left, the right hand panel at the bottom panel on the right hand side of the screen, here you see the stress building up slowly, and then it reaches a critical value, then it drops, and then again it rises and drops. Well, this is a very simplistic picture. A more realistic picture is the one that is shown below. However, this is business as usual. Now, what happens if you induce human-induced changes into the stress regime in the subsurface, for example, by all of those processes? So, the stress levels, they don't rise up to the red line there on the right-hand panel at the bottom. They do not get to reach those critical levels, but before that, the failure is affected, rock failure is affected because of other changes that take place. And that is really important, because if you leave it as business as usual, an earthquake may happen at recurrence intervals which my previous speakers mentioned in hundreds of years. But in this case, when you induce changes by man-made interventions, then it can actually lead to failure quite frequently. And that is what we have seen at a number of places in the world, but most importantly in India, in the Koyna region of Maharashtra, where a huge reservoir was built, and it's absolutely important to have the reservoir, but it also led to enhancement of seismic activity there. So then I'll briefly talk about what we mean by triggered versus induced earthquakes. There's a slight difference. Basically, both comprise anthropogenic seismicity. And then I'll show the global distribution and the underlying mechanisms a little bit. I'll talk about what we are doing in Koyna, and I represent the Borehole Geophysics Research Laboratory of the Ministry of Earth Sciences, and I'm really proud to see that Dr. Naik is chairing this session. He has really supported the development of this research laboratory and taking up such a huge program in the country. And Dr. Ravichandran, current secretary, has been supporting us to carry out this program. And lastly, I would also dwell upon a little bit how do we use our current understanding acquired through research in objective hazard assessment. So, what are are the different kinds of human activity that cause induced or triggered seismicity? Many industrial activities, and there are really many. And what they do is they alter the stress distribution in the subsurface. By the changes that happen at the surface, the stress levels in the subsurface are altered, and that in principle can induce earthquakes, although most do not. So there are geologically favorable conditions where the earthquakes are induced, and in not so favorable conditions we will not expect earthquakes. So industrial operations such as water reservoir impoundment, that is dams basically, which are needed not only for hydropower production but also for flood control and irrigation. Then there is underground mining. So a lot of excavation that takes place in the mining activity can lead to inducing earthquakes. Oil and gas production, when you extract oil and gas from the subsurface, you basically cause some kind of a subsidence and the resulting impacts from that. Hydrofracturing from shale gas exploitation, for example, that's widely prevalent in North America, but also slowly catching up in the country, in our country. And there what is done is we inject fluids at high pressure to create artificial fractures in the subsurface, in the crystalline basement rocks, hard rocks. And that often leads to seismic activity. And when that seismic activity, although it's not of a very high level, but it does create panic, as Chairman mentioned a few moments ago. Wastewater disposal, that's an important thing. In oil and gas industry, there's a lot of brines that come up along with the oil. Now, where do you dispose them of? So you have to inject them in the subsurface. That's the best alternative, best scenario that is available today to us. And that again involves injection of the fluids into the subsurface, and that can cause stress levels to change. And then geological sequestration, so in burning of the CO2 gas inside. So as a general rule, the deeper the activities are, the larger the stress alteration is, and the closer the seismogenic faults are, the more likely the earthquakes are. So it's just not one, but number of conditions that need to be favorable. And also we have seen that the largest number of induced seismic events at global scale have been related to mining operations. But the largest induced events in terms of magnitude are related to water impoundment, that is reservoirs and dams. Briefly, by induced seismicity, what we mean are these events are entirely controlled by these stress changes caused by human operations. So humans are totally responsible for induced events. Whereas in triggered, there is an underlying reason. For example, the tectonic stress that plays a primary role, whereas the human activity adds a trigger. So contributes for a small fraction of the stress change. So that's very important to understand. For example, if you have a reservoir, water reservoir, then basically a geological fault or a plane of weakness is there. And that might lead to earthquakes in the natural sense, but in several hundred years. But if you add the reservoir load there, then the trigger from that might lead to very frequent seismic activity. So that's the case of triggered. Whereas in where you inject water into the subsurface, even in a seismic area, you can actually cause induced earthquakes irrespective of whether you expect it there or not. So and there are many workers who have worked in this. For example, in India, we have the work of Dr. Gupta, who gave criteria for discriminating the reservoir-triggered seismicity from natural earthquakes. Essentially, one major common criteria is the spatio-temporal correlation between seismicity and industrial activities. So if you see an area where there was no past seismicity, but after the introduction of a particular kind of industrial activity, the seismicity level dramatically changes. So that's a very clear indication that we are seeing anthropogenic or a triggered earthquakes scenario. And then there are other ways to discriminate these earthquakes from the natural earthquakes. So if you look at the global distribution of induced and triggered earthquakes, you can see they can occur really anywhere. Really anywhere. And here you see they occur in all continents, and they occur, if you see the right hand panel, so they can occur from dams, oil and gas, geothermal, wastewater, mining activity, and these are all color coded, so you can very easily identify them. And here we have Koina towards the center and towards the bottom of the figure, where in India we have a really big, earthquake, magnitude 6.3, which, as if you have seen Sumer's presentation in the intraplate, it's a quite big earthquake, and that happened primarily after the impoundment of the Koina reservoir, the Shivaji Sagar reservoir in Maharashtra, which today produces 2,000 megawatts of electricity to the national grid. So it's really important, but it has its causes. Now, if you look at the distribution of anthropogenic activities by source, you can see almost half, or just about less than half, are caused by mining activities, and about a third are caused by water injection, and less than a third by water reservoir impoundment. So essentially, this is the area, this is the scenario in which we are working. And if you see on the right hand side, the maximum observed magnitudes of the different anthropogenic activities are plotted, and you can again see that the water reservoir impoundment causes the maximum observed magnitude for such anthropogenic activities. If you look at the bottom, the largest earthquake induced by fluid injection, currently everyone knows about Oklahoma in the US, where these wastewater are being injected in the subsurface, causing big earthquakes, as big as 5.8 magnitude, which is really big in terms of where you did not have any seismicity. Then Koina is the largest earthquake triggered by water reservoir impoundment anywhere in the world. Then in Ghazli in Uzbekistan, the largest triggered earthquake by mass removal. So we can go on. Now, what is important here is to realize that the stress released in an induced earthquake is the anthropogenic stress, that is the the anthropogenic stress that we add by the human activity acting on the pre-existing stress. So, and the minimum amount of stress that is required to modulate such activity is really a few hundredths of a megapascal. So it's really small, and therefore these can really occur anywhere. The largest magnitude induced by an industrial activity is proportional to the scale of the activity, the scale of the fluid injection pressure and rate, etc. Now, if you look at the mechanisms, I'm not going into detail, but basically the changing of the alteration of the subsurface stress field, and you reach certain critical thresholds, and then you can trigger these earthquakes. There are different settings, and I'm not going to great detail, but essentially stress is a key parameter when we talk about earthquakes, and the stress in the earth, inside the earth, the stress field we need to understand, and that really gives us a clue to distinguish between the different kinds of triggered earthquakes. Then we have the reservoir triggered earthquakes, where you have a big lake, and the load of the lake, the pore pressure, the water percolation from the reservoir, all of these can play in very different ways and interact with the stress field and cause the failures in the rock mass. Now, how can human-induced earthquakes be controlled or reduced? This is an important question, because if we are inducing the earthquakes, then we definitely would have some way of controlling them, or at least reducing or minimizing them. So, but that requires the modeling of triggered seismicity using near field information, and that is the key to understanding the various controls. One must realize that induced earthquakes is inherently a multidisciplinary area that involves all different aspects of geology, geophysics, seismology, rock mechanics, modeling of complex systems, etc. So this is, overall you can say it's seismology, but yeah, you have to realize that this is a very multidisciplinary area where all fields of earth sciences are extremely important. And if you can see from this figure, you need all these different parameters to constrain, to understand, to model the system. And many of these parameters you can get only through deep drilling. You have to measure deep inside the earth where you have the faults, or by doing advanced laboratory experiments on the rock samples that are recovered from the fault zones at depth. This gives a scenario of the various kinds of data sets. I'm not going through them. I think I'm going to finish it quite quickly by summarizing a result that we have done in Koina. So Koina, if you see the left panel at the bottom left panel, we have the Koina Dam. The dam has a height of 103 meters. It has a reservoir volume of 2,800 million cubic meters. So it's a huge dam, and you can see the seismic activity that this has caused. You can see the Koina reservoir in the north, the central central panel. You can see the map of the Koina region, where you have the Koina reservoir and you have the Warner reservoir in this south, and you have the seismic activity that is shown here. Now, this seismic activity is very well established that it is related with the changing water level. So the annual loading and unloading cycle of the reservoir. Loading cycle because of the monsoons, unloading cycle because of the post-monsoons. And therefore, the Ministry of Earth Sciences took up this program of scientific deep drilling, where we have now drilled up to 3 kilometers in the region to acquire lots of various kinds of data sets that are extremely important to understand this process. And you can see here we have already got a lot of data on geology, geochemistry, rock mechanics, in situ thermal structure, stress, etc., through which we are now able to analyze these huge data sets that have come from this deep borehole experiment so far. And the main conclusion that we are able to say about Koina from such studies, and that's extremely relevant, is that in Koina we have a favorable condition for earthquakes. Geologically, there is a favorable condition for earthquakes to occur due to the presence of optimally oriented, critically stressed, hydraulically conductive fractures. Small changes in fluid pressure and or frictional strength could provide the necessary trigger for failure. And for further constraints, we have to go for further deep in situ measurements that we have planned, and also the laboratory experiments that also we have planned. So this is the deep borehole observatory that we have planned, and this will possibly become a reality in the next few years. The last slide is, how do we use our current understanding acquired through research in objective hazard assessment? And this was an important area which was put forward in the workshop note, the concept note that was circulated. The main thing here I would like to say is our understanding of the relevant processes and the site-specific conditions that matter, that is the location of faults and their stressing state, is yet incomplete. The chairman made a mention of this, and I can say very clearly that this is the central area where we need to improve. But there are also other things that we can do, because a comprehensive risk governance strategy must include also a suitable monitoring infrastructure wherever you have such industrial activities, a sophisticated data analysis technique for real-time seismicity characterization, quantitative risk analysis, and transparent decision protocols. Many of these we are yet to do actually, but they are necessary. And this will allow us to evaluate the system response before the occurrence of critical events, before it's too late. Yes, thank you. And okay, so we need some more additional data and modeling efforts. I'm not going into this. So the final take-home message is, human activities can have a real impact on earthquake occurrences with various mechanisms that impact stress conditions. Triggered earthquakes are becoming more and more frequent, and you can see the number of research publications over the last 60 years, and you can see the rising number of publications in the last 40 years or so. Induced seismicity is inherently a multidisciplinary process, and we have to treat it as such. We still have an incomplete understanding of all the relevant processes, But the programs such as the scientific deep drilling in Koina are crucial to develop a comprehensive understanding of the mechanisms and assessment of the associated seismic hazards. That's the message that I wanted to share with you. Thank you very much.
Thank you, Sukanta. May I now